just take this off and unplug it from the back of there, but this is really a pain to take off.
Okay, let's stop the. Welcome to class. We're at week 4. What is significant about week 4? It's the last material before the exam. So upcoming thing to consider is that the exam opens on Friday. I have assumed that one reason for someone to take a Salt Lake Center class is maximum flexibility. So there's quite a lot of flexibility in the number of days that the test is open. It stays open through Tuesday. Most students, that means they take it Monday night or Tuesday and pay the late fee. But you could take it Friday or Saturday if you want. Just depending on where you take it. How many of you have taken exams at the Salt Lake Center Testing Center? How is it?
Really, really quiet.
Really, really quiet.
I was the only one in there.
Yeah, that's common. You might be the only one there. There's not anxiety leaching out of the bricks of the room as you sit there, which is nice. So I actually have had Provo Chem 106 students who, after they've taken an exam in the testing center, choose to get on the train, review the material till they get here, take the exam here, and then take the train home. Obviously, you can choose to do it however you want, but some people consider. I even had one student that turned out the testing center here was so much better. He was a veteran and had PTSD. And when he was in the testing center in Provo, every time the proctor or someone else would walk up behind him, he'd have an anxiety attack and break his sweat. Didn't help his test performance. And we figured out that he could, that never happened in the Salt Lake Center. He'd sit in a corner even and nobody was behind. Okay. So the test is a mix of multiple choice and short answer. I write the tests. I also write your pre and post lecture quizzes, and I write your recitation questions. So even if I'm not trying to make the test look like those other things, I can't help but write the same kinds of questions the same kind of way. Most students have given me feedback that they don't think that there was a lot of surprises on the test. I'm not a professor who believes that I should teach you one thing and then test you on how tricky you are at thinking of things new ways on an exam. I actually think that's kind of rude. There's a lot of nodding. Let me say that professors tend to think that if you understand the material fully, thinking about things a new way is not a problem. I don't agree with that. I think that by throwing completely different things at you, and it doesn't mean I'm going to ask you exactly the same questions, but asking you to think creatively in crazy ways on an exam at some level is not testing your understanding of the material, it's testing your ability to think creatively under conditions of anxiety. And that's not what I think my test is supposed to be investigating. Okay, so if you are comfortable with the recitations and all the questions that we did in recitations, you could ace all of the pre and post lecture questions. They make sense to you. The examples we've done in class and the kinds of questions I've asked you to discuss and draw and explain to your neighbor. If all that stuff that we're doing in lecture you're comfortable with, needs to be just fine. The mock exam is designed to be on the same scale and type of questions as the multiple choice. So there are 2 ways to take a mock exam. What's one way to take a mock exam? One way is to take it closed book, closed note. Why would you want to do it that way?
So you can see what you actually know.
You want to see what you actually know, because each of us have had the question where we feel like we have mastered the material and we're comfortable with it. And then we go take the exam and the exam says, actually, you didn't know there were some things you missed. The mock exam is designed to let you catch those things before you go into the exam. Okay, the due date is set Monday at noon. The reason I have set the due date Monday at noon is, when do my Monday office hours start? Noon. I want you to take the mock exam in enough time that you can come to office hours or go to the Chem 106 lab and figure out what you did wrong, so you can fix it before the exam. Yes.
How much does the mock exam count, or does it count against you?
It is worth very little. And take it, I think, 3 times, 4 times. So if you're using the mock exam the way it's designed to be used, it cannot hurt your score. The goal is to correct those things, right? Yes.
Sorry, you already said this, but how long do your students normally take to finish?
I have scheduled, like they always ask you on the testing center software, how long do you think it's going to take? And I wrote 2 hours. Some students are going to do it in an hour and a quarter. Some students like to keep looking at the paper until they finally feel enough diminishment of anxiety that they can stand up and turn the exam in. Okay. If you are a slow test taker, make sure that you eat and eat some protein and maybe even some fat before you go into the exam. How come? What does your brain exclusively metabolize? Your brain only uses glucose, right? If your blood sugar drops over the course of the exam, what happens to your brain function? Plummets. The first time I taught Chem 105, the second or third exam, and I asked the students, do you want a shorter exam that doesn't cover as much, so you kind of have to choose, you hope that what you know best is what shows up on the exam, or do you want a longer exam that covers the material more thoroughly? What do you want? And the whole class said, we want the longer exam. And so I wrote a longer exam. And as I graded this long exam, I could see over the course of the exam, the closer and closer it got to the end of the exam, the stupider students got. And I don't mean stupider in terms of base intelligence, right? I mean, I could watch students that I knew understood that material make stupid mistakes. And that's because you get tired and your brain glucose drops. Now, if you're like climbing a mountain or, running, your blood glucose drops and your body gets the cue to start converting glycogen to blood glucose and you're fine, right? But for a certain percentage of people, probably me included, if I'm sitting there in my chair, no matter how much blood glucose I'm using, my body might not get the cue because I'm just sitting there, right? But you want to create a situation where your body is prepped to perform according to your potential. So eat. That sounds like a stupid thing to say, but it's easy to get so focused on preparing that eat and sleep sort of isn't something you think about. Actually, because of the nature of this material, you have to think about a lot of things at once, right? And you have to keep track of equations and symbols and positive and negative signs. And if this goes up, this goes down, which makes this go up. That's fairly brain complex thing. And you're all capable of it, but it's really easy to make a mistake, right? So you want to be in top form so that it makes it more likely that your exam performance actually reflects what you know instead of just all the ways that you could blunder in that particular mode. Okay, it's set to use any calculator. Every equation that you're going to need is on the exam and give you the exact equation sheet to study from that's going to show on the exam. It's given in content. Also, last page. And you'll notice that the equation sheet doesn't tell you anything about which equation is which. You have to recognize that, but I have full confidence that you can handle it. Okay, lots of resources available. Obviously, the lecture slides are posted. There's little snips of me talking about different elements of different lectures. There's also all of the Professor Dave explains different things. If there's something that you know that isn't quite fitting in your brain, it's entirely possible that now you're smart enough that when you go back and watch material that you watched before, you'll see all sorts of connotations and meanings and connections that you missed the first time. I do like the Melanie Cooper Clue textbook. And many of you have not realized that if you open up the Gilbert textbook, first of all, it will not radiate and kill you. It's okay to open it. And the end of the chapter actually has a really useful summary with all the equations and the kinds of problems you'd be asked to do and what the pictures would look like and what the graph would look like. And one of the newer authors of the textbook is Stacy Bretz. So it's the Gilbert textbook, and then there's 2 or 3 other people. And the last author right now is Stacy Bretz. She is a chemical education researcher who studies university level education and what are all the ways that professors do things wrong so that students get it wrong. And she has incorporated all of the molecular level pictures and some of the diagrams. If you open up the back of the chapter summary, they're kind of review questions that are actually really good study things that are designed to help you make them. Okay, we haven't prayed, have we? Let's do that. Pray for us.
Kind and gracious Heavenly Father, we thank thee so very much for this day and for the opportunity that we have to be here together to learn and for this environment. And Father, we're so grateful for thy truths that thou hast brought and taught to us, and that we can learn to more fully comprehend thee. And Father, we ask thee to please bless the Spirit to be with us, and we love thee and we say these things in the name of Jesus Christ.
Okay, let's do some review here. Review at the beginning of class. Okay. What I notice is because this information and this class is about how all the ideas fit together, that's not a trivial intellectual pursuit. And sometimes the first and second and third times that you look at the material, you're still trying to process the individual pieces. And it's not until you're comfortable enough with the individual pieces, you don't have to think so hard about each little piece, that you can actually see how the pieces fit together. So I review at the beginning because the likelihood of you being able to put all those connections together in more effective ways goes up. Okay. So what we've done so far is we've talked about the rates of reactions, and we have a rate law or a rate expression or a rate equation here. We talked about that. And last lecture, we talked about how the rate constant itself reflects a whole bunch of things that are happening in the reaction, including what the energy of activation is, what the temperature is, this thing called A. Okay. Our ability to understand the rate law and what's happening and what affects the rate law depends in part of our understanding of what happens when a chemical reaction happens. And for this, we use the energy diagram, right? So we have starting material potential energies, we have our product potential energies, and we go through a high energy transition state on the way from starting materials to product. Now, the transition state is what the molecules actually look like in terms of structure and bonding or lack thereof, halfway between. Okay. Talk to me about these questions. Ask your neighbor. Those 3 questions.
Next one. Distribution. And where like similar so what? Yeah, not all of them. See a lot of them up there though.
Determine the fraction. So I don't think I have enough energy to react.
Tokyo.
Yes.
Image that can help answer the first question: do all molecules collide with enough energy? So molecules have to
That
collide
question in the
with
test, right?
enough energy. It starts here, make it over this barrier. They don't have enough energy. They're going to make it over the barrier?
No, man.
No. So if you have a sample of molecules, there is a variation in how fast those molecules are moving. This means there's a variation in how much energy is available to those molecules to go over this energy of activation barrier. So for a sample of molecules, depending on what the energy of activation is, only some of them will have enough energy. So here we have this red curve and the green curve. The curve reflects the number of molecules with a specific kinetic energy. So as you go farther on the x-axis, the molecules depicted there fall under that part of the curve will have more energy. At lower temperature, you can see that, what do you notice about the distribution? More of the molecules have less energy, right? As you increase the temperature, more of the molecules have higher energy. So if you have to have this much energy to make it over the energy of activation barrier, what about all the rest of these molecules? Are they going to react? No, they're not. Only the molecules that have high enough kinetic energy, that are moving fast enough, can make it over the energy of activation barrier. Okay, so if I'm looking at the green line, only the ones, like only molecules here have enough energy to react, right? If I want to increase the percentage of molecules that have enough energy to react, what do? Raise the temperature. Yeah. So do all molecules collide with enough energy to react? No. This, when we look at the Arrhenius equation, this factor e to the minus e over RT, that tells you for a given energy of activation at a given temperature, you end up with a number that essentially represents the fraction of the molecules that will be able to react. If the temperature goes up, that fraction will go up. Okay, so what determines the fraction of molecules that have enough energy to react? Well, it depends on the energy of activation and the temperature, right? If the energy of activation is lower than at a specific temperature, what will the fraction be? So at a high energy of activation, you're likely to have a lower fraction of molecules that can make it over that barrier. You raise the temperature, the fraction will go higher. And that fraction comes from the E component of the Arrhenius equation. Okay, so what's A?
If those ones that have the energy that will make it, so like another subset.
Okay, so this part of the plot says what fraction have enough energy to react? And A tells you how many collisions will lead to product if there is enough energy. So think about this. So what's A? A is actually a number that tells you how many collisions per second would happen and lead to product if the temperature was high enough that all of the molecules could make it over the energy barrier. So A says, let's assume that all the molecules have enough energy. Does that mean that if they have enough energy, are they all going to lead to product? Well, that depends. And what it depends on is in part, some collisions have to happen in exactly the right spatial orientation. So one part of a molecule has to overlap with exactly the right part of another molecule. And if they hit backwards, what happens? Nothing, right? And so A includes an idea. So A comes from the number of collisions there are per second, and also the fraction of collisions that happen in the right orientation. So A equals Z times P. You don't have to know that. What you have to know is that A reflects both the total number of collisions and the fraction of collisions that happen in the right orientation. In terms of us trying to figure out the mechanism, it's the right orientation, a requirement for the right orientation that matters. Okay, so if you'll get product no matter how the two molecules collide, does that mean your A is higher or lower?
Say that one more time.
Okay, let's say it a different way. Suppose in order for a reaction to occur, you have to have orbitals lining up in exactly, precisely a specific orientation. What happens to A then? Down, right? Okay, and the opposite thing can be true. If any possible orientation of collision could lead to product if the molecules had enough energy, what would happen to A? It would go up, yeah. Okay. Does A change its temperature, or do we assume it's a constant? If we think about how we study this reaction, we're assuming it's a constant. So how do we get the values for A in energy of activation? Experimentally. Experimentally, we take the equation, natural log of the rate constant equals is a form of the Arrhenius equation where we take the natural log of both sides and then rearrange into the equation of a line. So we call this the linear version of the Arrhenius equation. It's expressed in the term y equals mx plus b. When we plot log of k versus 1 over t, can we get the A value and the energy of activation? How do we get the A value from that plot?
Y-intercept.
So we can find the equation of this line. The y-intercept of that equation is the natural log of A. And we can take e to that value and get the value for A. Okay, if we're doing it that way, we assume that there's one value of A that applies over the whole curve, over all the temperatures, right? So we're assuming it's a constant. It's a little bit tricky. Can you click the screen for me? It's a little bit tricky because if you increase the number of if you increase the temperature, you are going to at some level increase the number of collisions. But the difference in number of collisions over the temperature range that we typically are measuring for these experiments is small enough that we're assuming that A is actually a constant. We're close enough to a constant over the temperature range we're working with. Treat A as a constant, which means when we change the temperature, we're assuming that A doesn't change. Yes.
This might be backtracking a little bit, but on the previous slide, I had answered the determines the fraction of molecules. I had answered about orientation. So why does orientation affect A and not the fraction of molecules?
Okay, because there's really multiple things going on here. If we look at the energy, molecules have to have enough energy to make it over the peak, right? And the fraction of energy of molecules that have that much energy is calculated from the Arrhenius equation. It comes from this e to the minus EA over RT term. So can you see, as the energy of activation goes down, you'd have to have a higher temperature in order to have a high enough fraction. Okay, but that's not the only thing that's going on, right? Because you can have molecules that have enough energy to react, and when they collide, they still don't react because maybe they're colliding backwards, right? And that shows up in this A value. So the Arrhenius equation includes everything we know about the energy diagram and how much energy you have to make it over the energy barrier. That's in this e to the minus EA over RT. And then if we say, yeah, well, that's not the whole picture. Conceptually, we know there's more to it than that. Everything else that isn't that shows up in the A. And the one that we most care about in terms of understanding mechanisms is how the collision happens. Does that make a difference? Because that tells us about the orbital overlap that's required for a reaction to happen. In Chem 105, we talked about valence bond theory and how if you overlap orbitals, that makes a bond. Remember that discussion? That whole idea of the geometry of overlapping orbitals shows up in the A term. So if you can connect everything that you've learned, it's really quite amazing how if you know how to read the math, it contains so many different concepts, right?
Yeah, I'm about to get that tattooed on my body.
Yeah.
So with the equation, the linear one. So if the y-intercept value is 22, do we do to get a, okay,
Okay, suppose the equation of the best fit was this, right? From that equation, we know that the y-intercept equals 22. And we know that the y-intercept equals, right?
okay,
So how do we solve for a?
e to the 22.
Yeah, so a equals e to the 22.
Okay.
So we get out our calculator, calculate 22, and that's the value for a.
Okay.
How do we calculate the energy of activation then?
Times the slope by r.
So the slope is equal to minus EA over R, which in this case equals 2, right? So the energy of activation, we have to multiply both sides by -2 to get rid of the negative sign. So we put -2 on that side times R. What units do we report energy of activation in? Joules. What units do we report A in? That's a good question. It doesn't necessarily have. Okay. So what affects the rate constant? If we're looking at the equation, what affects the rate constant is the fraction of molecules with enough energy to make it over the energy of activation. And total number of collisions, which is included in the calculation for A. And the fraction of those collisions that have the right orientation for reaction, which depends on the mechanism. Also included. What A is the total number of collisions multiplied by the fraction of those collisions that actually happen in the right way, that they could make it over the energy barrier. So what K equals is the total number of collisions in A times the fraction of those collisions that are going to collide in the right way that could lead to product, also in A, times the fraction of the molecules that have enough energy to make it over the energy of activation barrier. And you multiply these three things together and you get the rate constant. So there's actually a lot of information conceptually embedded in the Arrhenius equation, which is why it's my second favorite equation. Yes.
Is the temperature supposed to be in that first one?
Yes,
Yeah,
it is.
okay.
Good call. What's missing here? Temperature is supposed to be in the numerator, in the denominator, so I need to fix that. Make a note on your notes that I am amazed at the degree to which I can look at slides and be thinking about the concepts and miss actual digits that are written on there. It's like my brain substitutes what's supposed to be there. So I appreciate you pointing that out. Okay. Now we can express the Arrhenius equation as the straight up original Arrhenius equation, right? But there are times, so mathematically, if we, the Arrhenius equation, one way to read it is to say what happens to the rate constant as you change the temperature, right? So a scientist will always visualize that by drawing a curve. So what happens to K as the temperature goes up? I actually had to look this up before class. Erin looked it up for me because I couldn't remember what an E curve looked like. Remember all those high school experiences where you had to plot the different curves and what the shapes were? How many of you remember those? I didn't. Why did they make you do that in algebra?
In chemistry.
So when you got to chemistry and you had K equals AE to the something, actually K is a function of minus EA over R over RT. You can see what the curve looks like. Actually, since it's a negative exponent, that means the T, if you take out the negative exponent, the temperature should be in the numerator. which would make the curve look like that. Okay, take home message, K goes up with temperature, right? But if we look at a plot like that, that doesn't help us come up with the energy of activation or the A value, right? But if we take that Arrhenius equation and we express it in the linear form, then we can actually measure our rate constant at different temperatures and analyze that data to give us the energy of activation and the A value. And how useful is that? I think that's really useful. Okay. We can also take this linear version of the Arrhenius equation and subtract the equation at one temperature and one rate constant from the equation with the different temperature and rate constant. End up with this. Now, there's a couple of different versions of this equation. They look different. Some of them have the minus or the reverse T2 and T1. They're all just versions of each other. Okay, question. Ask the neighbor, how do you know which one to use?
Isn't the third one you have like temperatures and control? Different temperature.
Like what the third one is, like the.
Let's get in that one, but I just like
One at.
the other two. For the rate constant.
Oh, yeah, you don't need.
Yeah, they're the
solve.
same.
So this is what I would say.
Let's see what she says.
The first one and the second one are the same equation, just in different forms, right? You can use whatever one you want. Now, typically, if you're solving for anything in the equation, I would think that the linear form was easier to use. And if you think about the kinds of sample problems you've been given and the smart work problems, chances are, anytime you had to numerically calculate something, you use this one. And if you're ever presented with a plot of natural log of rate constant versus temperature, this is a wonky way to plot something, right? Like, why would anyone plot natural log of something versus 1 over something else? Right? Like, what the heck? The only reason to do that is because we have an equation that allows us to interpret it. This is an Arrhenius plot. If you ever see an Arrhenius plot, little alarm bells should go off in your head. And what will the alarm bells say? Equation, equation, right? If you ever see data plotted in what seems like a convoluted way, natural log instead of K, or 1 over T instead of temperature, you should know that, of course, chemists are only plotting in a weird way because there's a weird equation that allows you to interpret it. Okay, so if you ever see an Arrhenius plot, use this form. Okay, Arrhenius plot requires a whole bunch of different, like this line comes from a set of data, right? So maybe something like that, right? So you have to collect a whole bunch of rate constants at a whole bunch of different temperatures. How do we collect rate constants? Lecture 2, how do we come up with a rate constant? You either have to do the integrated rate law analysis or you have to do a method of initial rates. And then you have to do that at a whole bunch of different temperatures. Is any chemist going to be excited about that? A lot of data collected, right? So if you want data that's maybe not as thorough, but a lot faster, what we do is we take the linear form, subtract it from itself and simplify, and you get the 2-point form of the linear Arrhenius equation, which allows you to just measure your rate constant at 2 different temperatures. So K1, you measure it at T1, K2, you measure it at T2. And from that, you can calculate the energy of activation. Or if you know the energy of activation and the rate constant at one temperature, you can predict the rate constant at another temperature, right? Okay, so work on that one. Yeah. Maybe didn't work. Try again. If you have an Arrhenius plot like this, which equation are you going to use? This one. If you have 2 K values and 2 temperatures, which one are you going to use? If you're asked to calculate A, which ones could you use? course, you can't use the 2-point form because it doesn't have A in it, right? So you have to use one of the other ones. Chances are you're going to use the other one. Okay, so in the last recitation, I showed you an Arrhenius plot, natural log of K versus 1 over the temperature. And again, why would anyone plot natural log of what we're thinking about instead of the regular form of what we're thinking about, unless there was an equation? When you see a wonky plot like this, Arrhenius plot, curve of best fit. And that is a beautiful line. Most kineticists wouldn't get 4 points that fit the line as well as that did. If they did, they might frame it. So from experience, when you're collecting experimental data, you're always trying to get experimental data that's good data. And when you get something that fits a line like that, what does your soul do? And when you get data that's all over the place and you can fit a line, but you're not sure that the equation means anything, what do you do for the next 3 days? It's a little ridiculous. The degree to which whether your data looks like that or not can make you happy or miserable. Okay. Let me tell you, the rate constant for the reaction is measured at 4 different temperatures. Does it matter what the temperatures were? Once you have the curve fit, equation that matters. Equation of the curve fit. Why does that matter? Because according to the Arrhenius equation, this number is equal to minus EA over R. So the slope can be used to get the energy of activation. And this number is the natural log of the A value. So the A value. Okay. So A says, using the plot, calculate the activation energy and the frequency factor. You just solve, use the slope to solve for A over R, and use the intercept to solve for the A. How about B? Estimate the rate constant at 318 K using the Arrhenius equation. How do you do that? So what we have here, this plot, we have this equation of best fit, y equals minus, I could write it so you could read it, minus 1387 x plus 22.67. What this equation actually means is the natural log of K equals minus 1387 times 1 over T plus 22.67. Okay, did the equation of best fit just give you an equation to calculate the rate constant at any temperature? Yeah. So the question tells you the temperature is 318 K. How do we solve for temperature is 318 Kelvin? Don't you love how many K's there are in street? Rude. Natural log of the rate constant, you just plug in the 318 Kelvin and you get a number, right? How do you get K then? Yeah. So you have a number that's the natural log of K, and you take E to whatever that number is, and that gives you your rate constant. I have had students say that they hadn't actually understood what math was for. 106. All that math training that you had, why you had it. So that when you have a relationship with things, you can test, change one thing on your x-axis, what happens to the y-axis. Hey, Karen, can you click on the screen? Okay. So if you want to see this solution again that we just did. Okay. We've done a lot of talking about plotting data, right? A whole bunch of plots. Why? What's the point of throwing all these plots at you? Say it louder.
It just gives us another way to interpret the equations.
What we're talking about is the trends. Change something, what else happens, right? That is a good way to do that. Now, what I've seen is a lot of Chem 106 students come in, and when they look at a plot, they say, ooh, it's a line. Curve. And they're focused on what the actual line looks like. When a scientist looks at the plot, what does a scientist look at first? The axes. Josh knows that because he actually works in a lab with, I mean, maybe you just knew that anyway. He works in my husband's lab. We go to group meetings together and talk about stuff together. First thing a scientist does is look at the axis. Why do you need to know what the axes are first?
What's changing what?
You have to see what's changing what. Okay, so go back to this question. What kinds of plots have we seen? What do they mean? And if I introduce them to you, you have to know them. So tell your neighbor what kinds of plots we've seen. It's not necessarily the same as a diagram. We've shown energy diagrams that help us conceptualize. When we talk about a plot, what are we plotting?
If it was the same as.
We're plotting data that we collected from a certain specific reaction. Okay. So now.
Like, I was looking at zero order for second order reactions, like the different equations that you could use to get a linear plot, but it depends which equation you use to get the linear and.
Good classic.
This is how I would answer the question. We started by talking about rates, right? And what is a rate? How do we measure rate? Change in concentration over time, right? So what we plot is concentration or right? What did that first plot look like? What typically happens to the concentration over time? It falls. Does it fall at the same rate usually? As we use up our starting materials, the reaction slows, right? So the slope, which is the rate at which the concentration is being used up, typically slows as well. And so the very first plot that we talked about was a concentration versus time plot that looks like that. Okay. That plot would correspond to a first order reaction. The concentration shows up in the rate law because as starting material is used up, that causes the reaction to slow, which means that times in the reaction, the rate is going to go down over time, right? Okay, but I also should that you might see a second order reaction. What does that plot look like? Okay. The rate changes more with concentration than it does for first order, which means that as the reaction progresses, what happens to the rate? It falls faster, right? And so what we see is, I'm not very good at drawing second order reactions. Probably still not curvy enough. It curves faster, right? Is that the only possibility for how concentration can change with time? What if we have a 0th order reaction where, as it turns out, concentration doesn't show up in the rate law? We can say the rate is equal to the rate constant. What would that curve look like for concentration versus time?
Straight line.
Straight line. It would look like a straight line. Yeah. Okay. So what we're actually collecting, the data that we collect for these experiments is concentration at a bunch of time points, right? But we don't actually, concentration is not the only thing that we care about. We care about rate. It'd be nice if we had an equation that could analyze this data. Wouldn't it be nice if we had an equation that said, what is the concentration as a function of time? Right? Wouldn't that be nice? How do we get that equation? integrate the rate laws and rearrange them to get the equation of the line. So if we want an equation that puts concentration on the y axis in some form, and time on the x-axis, what we do is we integrate the rate laws. The first order would be, we end up with natural log of concentration equals minus k times time. That's natural log of our initial starting material. Okay. If we collected data and wanted to analyze it with this equation, what kind of plot would we use? This equation, y equals m times temperature, slope times temperature. What kind of plot could I use with this equation? What would I put on my x-axis or y-axis? The natural log of my concentration at a given time versus time. And what does the plot look like? We have a negative slope, right? It's going to be a line. Okay. I can do the same thing with the second order reaction, only my equation looks different, right? A second order integrated rate equation looks like this. Oh, I did it wrong. This is in the wrong place, isn't it? Here's my second order curve. I totally did it wrong because I put my first order reaction. Keep it straight on your this is first order. In my head, I had space 0, 1, 2. I'm totally messing it up. So if this is second, okay, let's go back to this second order. I'm gonna rewrite it again.
Good, good.
Okay. If we have, so this one goes with this plot, right? What's the equation that goes with second order? Just drew in my 0th order position. This is second order. Over here. So if we were doing the integrated rate plot, what would it look like?
Positive slope.
The positive slope, the y-axis now is 1 over the concentration at a given time versus time. Why would we do it that way? It's one method of getting the order and the rate constant. If I start with a first order reaction, and I don't know that it's a first order reaction. I take the concentration versus time plot or data, and I plot 1 over concentration versus time. What will my curve look like? Will it be a line? It's only a line if the actual concentration versus time data came from a second order reaction. So if I get a line for plotting 1 over A versus T, I know it's a second order reaction. And what else do I know? If I know the slope, I know the K value. There's a question in the back first, and then.
I'm just wondering, so why the second order plot is a positive slope? And
That's
for 0 and for
When you work the integrated rate equation and rearrange it, the slope is negative. Do we ever have a negative K value? No. So if you notice, the first order slope is minus K, and second order slope is positive K. So we end up with a positive slope for second order, negative slope. 0th order. Concentration versus time curve. That is already in the form that we would use. In the right. Okay, yes.
In the second order rate law, the integrated form, part of it,
That was my question.
Sorry about that. Just in case you thought you were the only one that mixed up equations in your brain. That's why you have an equation sheet. So I recommend when you work a problem, when you write the equation down, do what I would have to do. And just double check that I'm not switching things in my head when I write them down. Okay. So quick, fast. Answer those questions for you.
Very exciting.
Concentration.
So things, concentration. And then. Your rate.
Yeah. I'm so fire. I know. We're gonna get on test like
Okay, so the rate law,
Very good.
if you can read the rate law with the Arrhenius equation put in, what does that tell you? Concentration affects the rate. As the concentration goes up, what happens to the rate? It goes up. Energy of activation affects the rate because it affects K, right? As the energy of activation goes up, what happens to the rate? It goes down. Temperature affects the rate. As temperature goes up, what happens to K? It goes up. What happens to the rate? It goes up. A, which actually in terms of what it tells us about a reaction, the higher the A value is, then we know that how the molecules collide makes a difference in terms of whether it will react. As if there is a requirement for a specific orientation in that collision for a product to form, what happens to A? It goes down. So what happens to K? It goes down. So what happens to the rate? It goes down. Okay.
So if the reactants affect the rate, does the concentration of the products affect the rate at all?
Okay, good question. So the rate law is expressed in terms of starting curve. At a certain point, you're going to come to equilibrium where the rate forward and the rate backward makes a difference. So the forward rate is only influenced by the product or the starting material concentrations, right? But when we look at a plot like this, what we see at a certain point is the sum of the forward and the backward rates, right? Is that affected by the concentration of product? Yes. Okay. We talked about catalysts last time, and we said a catalyst increases the rate. How does it do that? It lowers the energy of activation. Often that does it by making it go through a different mechanism, so you have a whole different energy diagram. Why does a catalyst not show up in these equations? Or does it? So the catalyst typically lowers the energy of activation. So it does show up in this. The other thing a catalyst can do is change the mechanism so that you don't have to have the same orientation required for everything. So catalyst can also change it. So while a catalyst does affect the rate and is not explicitly written into these equations, it's actually there because what a catalyst does is affect the energy of activation. Okay, next question. What does the rate expression and order have to do with the rate determining step of the mechanism? What's the rate determining step of the mechanism? It's a slow step. Where does the rate expression or the rate law come from? It comes from the rate determining step. So the stoichiometry of the slow step is what gives you your order. Okay. Okay, so in actual life, how do we know what the rate determining step is in the lab? We do the kinetics, we figure out what the order is, and then we extrapolate backwards to figure out what the rate determining step is supposed to be. Are you, as Chem 106 students, necessarily comfortable with doing that? No. So what do we do instead to have you practice the idea that the rate determining step is connected to the order? we work backwards. We say, here is the mechanism, here's the rate, here's the slow step, here's the fast step. Work backwards to come up with what the rate law should have been. Now, chemists in practice always do it backwards. We measure experimentally the kinetics to figure out the order and then figure out what the mechanism is. We're asking you to do it backwards because there's a certain amount of chemical intuition that's required to do it the other direction. If I told you that you were going to have to do that on an exam, a certain percentage of you would start to panic. Is that fair? And we're not putting you through that. Okay. Let's get that because what's more important? More of you and putting the pieces together or more moving through nuclear kinetics? Okay. So just tell me, if you're given the mechanism, if the slow step is the first step, how do you come up with the rate law? Just the order is the stoichiometry of whatever the reagents are in the slow step. But if the slow step is not the first step, if it's the second step, then what do you do? It's fine as long as the second step doesn't have an intermediate in it. How often does that happen? Usually the second step has an intermediate in it, right? And can you put an intermediate in a rate law? So what do? So we start out by saying this is what the rate law would be if we could include the intermediate, and then we have to find some algebraic manipulations to come up with a different way of writing the we did an example of that in class. If it's still making your head spin, come to office hours and I'll go through it again. Okay. Need a break before we start week 4. Okay, let's take a break. 5-minute break. And,
They don't write them in.
pause that. How do we know what kind of nucleus we have? What makes something hydrogen and something helium? The number of protons. So we call that.
Sorry, I just started the recording.
Okay, so the atomic number on the periodic table, what does that tell us?
Number of protons.
The number of protons. What tells us the number of protons and the number of neutrons? Okay, so there's this thing called atomic mass number, which drives me crazy because it's not atomic number and it's not atomic mass. It sounds like both of them. Physicists don't seem to have a problem with that. Chemists, I'm not the only chemist that just goes. So what's the way to get around that? Let's call it mass number. Why do we call it mass number? If a proton or a neutron has a mass of about 1, the mass number tells you both the number of protons and neutrons, the sum of them, and also the approximate mass, right? Okay, so when we talk about nuclear chemistry, we use the term nucleon. So we have protons and we have neutrons, right? They're both called nucleons. A nucleon is just one of those particles that we have in the nucleus. So a nucleon is a way to say proton and neutron together. So the mass number equals the number of nucleons in a specific kind of nucleus. Okay, now we have this idea called isotopes. If atomic number or the number of protons tells you what kind of nucleus you have, we can have different numbers of neutrons with the same number of protons. So for example, let's take chlorine, for example. Chlorine, the atomic mass on the periodic table, it's about 35.5. How do you get 35.5 when protons and neutrons only 1? There are different kinds of chlorines that have different number of neutrons in their nucleus. We call those isotope chlorine. So here's a picture. There are 3 different isotopes of oxygen depicted. How do we know they're all oxygen? They all have 8 protons, but oxygen 16. So the the lower number is the atomic number, which tells us the atomic identity. And the upper number is what? That's the mass number. Now, we typically refer to isotopes when we're comparing them by using the mass number. So we would talk about, we'd say this is oxygen 16, this is oxygen 17, this is oxygen 18. Have you ever heard that? Like if someone says uranium 238, uranium tells you how many protons are in the nucleus. That particular isotope has a mass number of 38. Okay, so the question of the day, do protons want to be close to each other? They don't. Coulomb's law says when you bring two positive charges closer to each other, what happens to the repulsive force between them increases as they get closer and closer together, right? How big is the nucleus? Very small. So what the heck is happening here? Can you imagine Rutherford doing the gold foil experiment and all of the calculations say that all the positive charge has to be compressed in a tiny, tiny space? Can you imagine his response? Probably his response was to say to his graduate students, that can't possibly be right. Go measure it again. And after they'd done that about 6,000 times, he had to believe it. And then the question is, how can you get protons squished together into this infinitesimally small space? Because what should happen?
Far away from each other.
They should totally come apart, right? And do they? Why not? There has to be an attractive force in the nucleus that is stronger than the very strong repulsive force between positive protons. What do we call that force?
Strong force.
Yeah, that's the nuclear strong force. Okay. Is this a case of chemists and physicists making up a force to explain reality? Yes.
Yes.
It turns out to be true, but that's how the scientific history went.
This is where we're looking for like the theory of everything, right? That like relates macro scale physics to the
Yeah.
atomic, but
Physicists are struggling with that one.
yeah.
That happened for a long time. Ask Einstein, who spent most of his life trying to do that, and it didn't work. Okay, so what does the nuclear strong force act on? Or another way of saying that is, what does the nuclear strong force act between? Question, nuclear strong force, attractive or repulsive? Attractive, and what's being attracted? Nucleons, okay? So the nuclear strong force attracts all nucleons to each other. That means the nuclear strong force attracts protons to protons, protons to neutrons, and neutrons to neutrons. So any kind of nucleon in very close proximity is going to be attracted by the nuclear strong force. Okay, the question is, over what distances does it act? It has to only act over very, very small distances, like you would find inside a nucleus. Otherwise, if you had two nuclei of hydrogen, if this nuclear strong force acted over strong distances, what would happen? The nuclei would slam in together and fuse. And is that what we see in chemistry? No. So the nuclear strong force only acts over very short different distances. Okay, is it stronger or weaker than electrostatic force?
Stronger.
On the distance scale of the nucleus, it's stronger.
And electrostatic force is what you're talking about, the protons that can't.
Yes. So what we have operating in the nucleus is a balance between repulsion between protons from the electrostatic force or the electromagnetic force and attraction between nucleons from the nuclear strong force. And that interplay between repulsion and attraction between those two forces is what determines the stability of nuclei. So when little primer here, what happens to the potential energy when things are strongly attracted to each other? Go up or down? What happens to stability when things are attracted to each other? Things that are attracted to each other, if they're experiencing a strong attractive force, they're more stable. So attraction increases stability, which does what to potential energy? It lowers potential energy. Okay. When you have repulsive forces, what does that do to the stability? It decreases it, which does what to the potential energy? Increases it. So we're going to talk about the nucleus as a balance between electrostatic repulsion, which decreases stability by raising potential energy, and nuclear strong force attraction, which increases stability by decreasing potential energy. Okay, so what we know about the nuclear strong force, at the distances in the nucleus, it tends to be stronger than electrostatic repulsion, but it can only act to a really strong distance. So here we have a picture where electrostatic repulsion should be flinging the nucleus apart, as the protons should repel each other. But what we actually see is the nuclear strong force acting between all the different kinds of nucleons, both protons and neutrons, holds the nucleus together. Here's a question for you. As you look at the periodic table, bigger and bigger nuclei tend to have more neutrons. So if we look at helium, 1 proton, 1 neutron, right? Neon, roughly, usually 10 protons and neutrons, right? But then you get to like cadmium. What do you see? More neutrons than protons. Indium, more neutrons than protons, until finally you get to very large nucleus like radioactive polonium. What's the ratio of neutrons to protons now? Super big. Why is that happening?
You need more of the strong force as you have more protons that want to be next to each
Yeah, it certainly gives the impression that the more the electrostatic repulsion between protons that you have, that the nucleus starts packing on neutrons to try to counteract that more and more. Okay, so can we visualize a nucleus? Kind of a funny question, right? Can we visualize an electron? I can't. I don't know about you, but I can't visualize an electron. So instead of visualizing a nucleus, when we say what does it look like, really we're saying, partly we're saying how does it behave. You know that nuclear strong force holds it together. Protons repel each other. You remember from Chem 105 and the de Broglie equation, matter has wave properties. Electrons have wave particle dualities. Well, so do protons and neutrons. All the weird, wacky, how do we describe position, wave function stuff that you'd have to do to describe electrons around a nucleus also applies to protons and neutrons inside the nucleus, including different energy levels. Remember in Chem 105 how electrons had lower and higher energy levels and they could absorb photons and move to a higher energy level and then emit a photon and go back down to a lower energy level? Protons and neutrons can do that as well. In fact, you remember from Chem 105 the whole range of electromagnetic radiation, and you get gamma radiation, which is the highest energy photon. Where do those photons come from? They come from a proton at a high energy level or a neutron relaxing down to a lower energy level and emitting a photon. Okay, remember in Chem 105, the Pauli exclusion principle, if you have an energy level and an orbital, only 1 electron with 1 spin, you can't have 2 electrons of the same spin in an orbital. The same principle applies to protons and neutrons in the nucleus. Really need to, am I going to test you on that? No, but I'm trying to communicate that all the weird and wonderful things that we did for electrons also apply inside. Okay, if we look at the periodic table, there's a whole heck of a lot of different elements, right? And if we say there are different isotopes of those different kinds of elements, how many kinds of nuclei are there? A bucket load, right? So the question of the day, are all nuclei of different elements equally stable? And are all isotopes of the same element equally stable? No. How would we depict the stabilities of different nuclei? So one way to do that is to say, let's plot the potential energy as a function of mass number. So here we have a particular isotope of hydrogen called deuterium. It has very high potential energy. How stable is that? Not so stable. Okay. If I get to helium, a typical helium nucleus, typical isotopes of helium-4, What happened to the stability of that nucleus compared to hydrogen? So this says helium is more stable than hydrogen, than deuterium. Okay, now this is how, as a chemist, I like to think about that. Nuclear chemists and physicists actually plot it differently. They plot the reverse. They plot what they call the binding energy, which is the energy of attraction between nucleons in the nucleus. When the binding energy is high, that means those nucleons are very attracted to each other, right? Which is the same thing as low potential energy. So these are actually different versions of talking about the same idea. Okay, tell your neighbor what the trends are. What does that plot tell you? What's the most stable? What's the least stable? What happens to stability of the nucleus as the mass number goes up?
Stability.
Oh, yeah, better.
Yeah, so. Sit. Right. It's to be one stable. Like less than a. Feel it's too big.
This is how I would express it. First is the idea that high potential energy means low stability and low potential energy means high stability. So where do we find the most stable nuclei? They're around mass number 56. The most stable nucleus is iron 56, which is in terms of the periodic table, not the lightest, but also not the heaviest. Okay. What you see if you're tracking the trends is if you have only a few nucleons in the nucleus, is that super stable? Why not? Is there a lot of attraction between those nucleons? There isn't, because there's not very many nucleons to attract, right? So the potential energy is higher and the stability is lower. As you begin to pack on nucleons, as the mass number goes up, there's more attraction between those nucleons, right? So attractive force correlates with high stability and lower potential energy. And as the mass number goes up, the stability goes up and the potential energy goes down. Then, as you add nucleons, as the nucleus gets bigger and bigger, what happens? The nucleus actually gets less stable. So it's more and more stable until you get to iron, and then after iron, the bigger it gets, the less stable it is. Another way of saying that is, as you go from hydrogen to iron, every time you add nucleons, you're making the nuclear strong force stronger more than you're making electrostatic repulsion stronger. Does that make sense? But then, as the mass number goes up, less stable, higher potential energy, which means as you go from iron up to the heavier elements, as you add nucleons, increasing electrostatic repulsion more than you're increasing attraction from the nuclear strong force. So the balance is different, right? What do you think that means about the distance over which the nuclear strong force can act effectively?
About the size of like a iron.
Yeah, the distance that the nuclear strong force can act effectively maxes out at about the size of an iron nucleus. After that, as you add more protons and neutrons, not all of the protons and neutrons that you're added can actually be attracted to all of the other protons and neutrons. Let me draw you a picture to help you visualize this. So let's assume, where's my drawing marker here? Okay, let's assume that this diameter is the diameter of iron, right? And that's the perfect distance for the range of the nuclear strong force. So that means if I have a proton here and a proton here, are they attracted? Yeah. Okay, now suppose I have a bigger nucleus. Tell me about the range of the nuclear strong force. That means that a proton here is attracted to the proton. I put a proton, if there's a proton over there, it might be attracted to this proton. Is it attracted to that proton? No. Is it repelled by that other proton? Yes. But when you get bigger than the range, the size of an iron atom, the nuclear strong force can't hold all of those nucleons together because it can extend over the whole nucleus. However, electrostatic repulsion can still repel over that whole thing. So the bigger and bigger you get, the more you're tipping the scale on the side of electrostatic repulsion instead of attraction from the nuclear strong force. So the nucleus is held together less tightly, which means the stability goes down and the potential energy goes up. Okay. Through confession, when you took Chem 105, we told you that the atomic mass of a proton and a neutron was the same as each other, right? What did we say the atomic mass was? 1. How many significant digits are we reporting in that 1? Yeah. Because we didn't want you to know that things are more complicated than that. If you report the atomic mass of protons and neutrons to 1, then we can say every kind of proton weighs the same as every kind of neutron. But if you report to more significant digits, what do we see? So this is a plot of average nucleon mass divided by atomic mass number. So instead of reporting the whole mass of the nucleus, we say, what is the mass of a single nucleon in different kinds of nuclei? So if there are 15 nucleons, then we take the nuclear mass and divide by 15. And that tells you how much does one proton or neutron weigh in that kind of nucleus. What do we see? Does a proton in deuterium weigh the same as a proton in an iron nucleus? No. So the mass of a proton in an iron nucleus is significantly lower than the mass of a proton in hydrogen. That mean it's a different kind of proton, or is a proton a proton? How can the proton tell what kind of nucleus is in so it can change its mass? What's actually going on? Notice the shape of this curve, right? That's the same as the shape of that curve, right? What does that mean? What that means is the mass correlates with the stability of the nucleus. A more stable, lower potential energy nucleus has protons that weigh less and neutrons that weigh less than a less stable, higher potential energy nucleus. So the mass actually reflects the stability. Okay, hold that thought. So the conclusion here is that protons and neutrons in highly stable nuclei weigh less. They have less mass than in less stable nuclei. So what's going on between mass and energy? Now in chemistry, what's the first rule of chemical reactions? Remember? Energy is conserved and mass is conserved, right? So the first rule of chemical reactions is that you get the same mass in products as you have in starting materials, right? That actually isn't true when we're talking nuclear reactions. And it isn't because of the relationship between energy and mass that was first formulated by who? Our favorite mid-20s prodigy, Einstein. You know how old Einstein was when he published Special and General Relativity, the explanation of the photoelectric effect, including the idea that light was a particle named photons, and also this equation, 26. Mind blowing, right? Okay, so he came up with this equation.
What am I doing?
What is the point of the equation and how does this apply to nuclei? What Einstein said, this equation says mass and energy can be equated, right? Or in other words, energy and mass are actually interconvertible. Interconvertible? That's the word I need here. It is possible to change mass into energy and energy into mass. That's what this equation says. Which Einstein had a gift for picking our scientific feet out from underneath us, right? What the heck? That feels wrong. It's actually true. Okay, so if we change the energy of an object, we can actually change its mass. And he first formulated that in the context of, if you take an object with mass and accelerate it really fast, or speed it up really fast, the faster it goes, the harder it is to accelerate, which means the faster the object goes, the more massive it is. And that was in terms of kinetic energy, right? The higher the kinetic energy, that some of that actually gets converted into mass. We're doing it in terms of potential energy of the nucleus, right? If the potential energy is higher, what can happen to the mass? Potential energy is higher. Higher energy means more mass, right? So go back to here. The most stable nucleus is this iron one down at the bottom, right? So what does that say about its mass? Most stable means lower potential energy, which translates to lower mass. That can be explained by Einstein's equation. Okay. So the mass of individual protons and neutrons in a nucleus can be used as an indicator of how stable or low energy the nucleus is. Which means if we have a nuclear reaction where we're changing starting materials to products, we're changing one kind of nucleus into another. When we change one kind of nucleus into another, we're going to change the stability of the nucleus, right? When we change the stability of the nucleus, what has to happen to the mass? It has to change, because when we change one kind of nucleus into another, we change the mass of the protons and neutrons inside that nucleus. So when we do a nuclear reaction, if we're creating a different kind of nucleus, the total mass is never conserved. What happens to the mass if you weighed all the starting materials and then you did the nuclear reaction and you weighed all the products? What would happen to the mass? We're only going to form nuclei that are more stable than we started with. Therefore, the mass will always go down. So mass is not conserved in nuclear reactions. The mass of the products is always less, the total mass, than the mass of the starting materials. Okay. So what happens? It's still all about the interplay between repulsion from the protons, the electrostatic repulsion, and how that adds up with the attraction from the nuclear strong force and size. So after iron, the nuclear strong force can't act over the whole nucleus. So as the mass number goes up, repulsion begins to be more and more important, which diminishes the stability of the nucleus, increases the potential energy, and also increases the mass of the individual proton and neutron. Can we just say that the real world is way weirder than we would have expected 250 years ago? Yeah. As mortal human beings, we have this idea that what makes sense to us should be what's true. And one of the shocking things about science in the 20th century, starting, 1903 and on, nuclear chemistry and quantum mechanics is actually, what is true is unbelievably weird. And often what is true is what we don't think is reasonable or what we wouldn't expect. Step back for a minute, from a gospel perspective. We want to use our reason and what makes sense to us as a gauge of what should be right. How good are we at doing that? Not so good. Yeah. So the interesting thing about studying science and the history of science is that just convinces me that if something doesn't make sense to me, probably it's my sense that's the problem and not the actual thing. Apply this to people studying church history. How many people have you known that said, I can't figure out what the point of plural marriage was? That doesn't seem right to me. Therefore, it can't be right. Therefore, I need to leave the church. And while I'm not trying to diminish anyone's personal struggle with any of those issues like that, the problem breaks down when someone says, this doesn't feel right to me, therefore it isn't right. Because what does science tell you? Lots of things feel weird and wacko that turn out to actually be bang on true. Quantum mechanics is one of them. The conversion of mass to energy inside the nucleus, for me, feels like one of them. Okay, so if you look at a periodic table, typically the ones you've seen have missing elements in them. And then there's all these ones that are outlined and not filled in. What does that mean? What are the ones that are outlined?
It doesn't exist naturally.
They don't exist naturally. They've been made in a particle accelerator. And actually, we can fill in all the spaces with ones that have been made naturally. Well, why don't they exist in nature? Like, why isn't there element 115 in nature?
It's not stable.
It's not stable. Why not? The nucleus is so big that the nuclear strong force can't hold the nucleus together long enough for it to be stable and exist in any real space and time because it's too big. Okay. And a lot of those, they made in a particle accelerator, and they checked them for a millisecond. And then they said, oh, we made it. Yes. And they get to be really happy and write a grant for $3 million and name an element after themselves and everyone's happy. But does it mean anything? It does to them.
How come number 61 isn't filled in, but then 62 one is?
People who study nuclear physics and nuclear chemistry, there are quite complicated rules about what makes one isotope stable and one doesn't. And for some reason, that one isn't very stable. And I don't understand the reason why. Okay. Somebody had a question. Maybe not. So what is a nuclear reaction? So what's a chemical reaction? You take atoms and what do you do to them? Pull them apart and connect them in a different way. But what are we doing when we do a chemical reaction? Do the nuclei change identity ever? No. What's changing? Essentially, we're changing where the electrons are and which electrons are shared between which nuclei, right? For a chemical reaction, we're only concerned about the electrons. A nuclear reaction, what happens in that? Changing the identity of the actual nucleus. Okay. Put this in the context of scientific history. Chemistry has its root in alchemy, right? What were alchemists trying to do? Transmutation, which is what? Changing one substance into another. When chemistry became a science, what's the first thing they decided? We're going to give up on transmutation because that is not even possible and it's stupid, right? So then when Rutherford and Soddy and other people started studying radioactive decay, what did they observe? Changing one kind of nucleus into another. So Rutherford and Soddy worked together at the University of Toronto before Rutherford came back to England. As they were doing the radioactive decay experiments, Soddy said, this looks like transmutation. And what did Rutherford say? Don't ever say that out loud again. But in fact, radioactive or a nuclear reaction is changing one kind of nucleus into a different kind of nucleus, usually with a different atomic number. So you're actually changing one substance. Okay. Now, we're going to talk about different kinds of nuclear reactions. One of them is fusion, where two smaller nuclei come together and fuse to make a bigger nucleus, right? also take a large nucleus and break it into pieces, right? Or it can break into two big pieces, we call that fission, or you can spit off an alpha particle. Okay. So this idea of fusion, two small nuclei could come together to make a bigger nucleus. Are there limits to what kind of nuclei can fuse? For example, when I take an iron nucleus, use it with something over here to make a nucleus maybe over here. What direction on this plot can anything go? So you can take small nuclei up here and combine them to make a bigger nucleus down here, right? Can I go the opposite direction? You always have to make something that's more stable and lower potential energy. So what kinds of nuclei could undergo fusion to create a larger nucleus? What's the largest nucleus that you're going to get using fusion? Iron. Yeah, you're not going to make anything more stable more than that. Because once you're there, maximum stability, you're not going to use to create that. And in fact, fusion is the nuclear reaction that happens in the core of stars. Our sun mostly is fusing hydrogen into helium. Larger stars can go on to fuse helium to make carbon and silicon, and ultimately the largest stars can make iron. And that's where fusion in stars ends. So scientists who look out to all of the stars and are trying to read the atomic spectra from the light released from those stars to figure out what elements are in the stars, the biggest one you can see is iron, and after that, you're done. Okay, how about fission? What kinds of nuclei on these plots could undergo fission? Just the big ones, right? The big heavy ones want to break apart to two smaller ones that are more stable. Okay, what's the difference between a nuclear reaction and a chemical reaction? So in a chemical reaction, electrons rearrange, so bonds rearrange, right? What happens in a nuclear reaction? Nucleus changes. How can a nucleus change? We can do fusion or fission. We also have radioactive decay, which is different than fusion or fission. In radioactive decay, either you have alpha decay, where you're spitting off some 2 protons and 2 neutrons, or beta decay, a proton can become a neutron, or a neutron can become a proton. So it's the nucleus that's rearranging and changing instead of the electrons. You end up with a different atomic number, and atoms and elements are not conserved. Really what we're observing is what Rutherford refused to call transmutation.
Sorry to go back a little bit, but does that mean that all elements heavier than iron came from like supernovas?
Yes. Okay, so it begs the question, everything that isn't, all of the solid things on this periodic table were actually detected on this Earth. If the Big Bang started with hydrogen and helium, and that's all we had, where did all this stuff come from? So the prevailing theory is that our Earth is actually pretty recycled. That any planet that comes together, if it came from a solar system, from a big star that could fuse to create all the elements up to iron, that's what that Earth would have. Okay. We have all these other heavy elements, right? And those can't come from fusion inside stars. So where did they come from? If you take the largest kind of star and it lives out its whole life to create all the elements up to iron, when fusion stops, because it's used up all of its starting materials, its temperature will fall. Because the temperature falls, it will begin to contract because its molecular motion will stop, which means the temperature goes down. As the temperature falls, there's this kind of rebound and it collapses and then explodes. And that's what a supernova is if you have a big enough star. The power of that collapse and explosion is enough that these nuclear physicists predict that that's where all these elements come from. So if we go out into the dirt of our world and find all of these elements, what does that mean about our Earth and our solar system? What that means is our solar system has to be leftover materials from a previous solar system with a super huge star that went through its life cycle, collapsed to create a supernova, which has then come together to reform our solar system. Okay, so what does that mean about the carbon atoms in your body? Where we used, right? The carbon atoms in your body come not just from the food that your mother ate when you were in utero, but they actually came from a previous solar system that ended up in a supernova and then collapsed back again to form our solar system.
What, like nuclear fusion that we like conduct as human beings, what's the biggest nucleus that we can create?
On Earth, we've only created helium. That's the biggest one.
Wow.
So chemical reaction, the atoms and the elements and the mass is conserved and energy is conserved. For a nuclear reaction, mass is not conserved. Which makes it a little hard to talk about whether energy is conserved, because if mass is being converted back and forth into energy, how do you talk about conservation? So what we say is mass energy is conserved. Whatever that sum of mass and energy together, that is conserved. Okay, a couple kinds of man-made reactions. The one that we do in nuclear reactions is fission. A common nuclear reaction or nuclear reactor reaction is you take a specific isotope of uranium, typically uranium-235. On its own, it isn't super stable. And if you hit it with one fast-moving, high-energy neutron, the neutron acts like a catalyst and catalyzes that nucleus to break apart into two different, smaller, although still pretty large, nuclei, xenon-140 and strontium-94. And when it does that, two more high energy neutrons are produced. Now, what in the normal chemical reactions we looked at, the catalyst gets recycled, right? Which means over the course of the reaction, the catalyst doesn't change its concentration with time, which is why the catalyst is zeroth order. What happens to the catalyst concentration over time here? It multiplies. Okay, so if you do one reaction, you get two high energy neutrons. How many reactions does that start? Two. Those two reactions start 4 reactions. Those 4 reactions start 8 reactions. Those 8 reactions start 16 reactions. What do we have on our hands? Out of control, right? Okay. So nuclear reactors have cooling cores and cooling rods and all of these things that are designed capture all except one neutron at a time so they can keep the pace of the nuclear reaction constant. And one source of a nuclear meltdown is that something malfunctions in that process, so they're not capturing most of the neutrons that are produced, so they can't control how fast the reaction happens. What's the other thing they have to control if they want to keep the reaction moving at a certain rate? What happens to reaction rate as a function of temperature? It goes up. So if something happens in the cooling system, then the reaction goes too fast and it goes out of control. What happened in Chernobyl is that the power to the cooling system was lost. And so it heated up. When it heated up, the rate was too fast for the system to keep up with, and it melted down. Okay. Does fission happen spontaneously in nature? It could happen if you happen to have a high energy neutron traveling at the right speed that happened to hit the exact right isotope of something else, right? How often does that occur? Yeah. Yes.
So where do the neutrons come from? Or like what causes them to?
Okay. What's the mass number for uranium? 235 nucleons, right? If we add up the nucleons in xenon and the nucleons in strontium, how many is that up to? 134. Number of nucleons has to stay the same. That extra neutron is one left over. It just happens that there's a neutron left over. Causes the catalyzed organ. Okay, so what we call an atomic bomb, they just have a bunch of uranium-235 and there's nothing to slow the reaction. And once it starts, it goes until when? Until all of the fuel is used up. How fast are the kinetics? Fast. Okay, we also can do fusion, which is what happens in stars, where you take the two smaller nuclei, speed them up in a particle accelerator so they're going so fast. Why do they have to be going really fast? What happens to the repulsion as those positive nuclei get closer and closer to each other? The propulsion gets stronger. So as they speed towards each other, what's going to happen to their speed? It's going to slow. If they're going to get close enough to each other for the nuclear strong force to pull them together, they have to start out moving so fast that the repulsion isn't enough to slow them and keep them from coming in close contact. Which means we have to speed them up super, super fast. Okay. So it's hard to do. On Earth, we've only done it with deuterium and tritium, or at least with hydrogen nuclei. Why would it be harder to do with larger nuclei?
Fast enough.
You can't get them going fast enough because the repulsive forces are higher. Would we want to do them with anything other than hydrogen anyway? What's going to give it, what kind of fusion reaction is going to give us the most energy out? Hydrogen. Because hydrogen is the least stable. So if we go from here to here, we get a lot of energy. Okay. So on Earth, we've only done this with hydrogen. And in fact, we have done it for what we call the hydrogen bomb. Why is it called the hydrogen bomb or the H bomb? Because it's a fusion reaction of hydrogen nuclei. How do we get that to happen? How do you get that started in a bomb? My understanding is they do a very small fission reaction to get it hot enough to get it to fuse. So why do we on Earth only carry out fusion with hydrogen? The problem with fusion is that you have to overcome the electrostatic repulsion to get the nuclei close enough to fuse. Hydrogen has the least amount of positive charge on the nuclei, so it's easier to happen on Earth. Okay, but other kinds of fusion reactions happen in stars. How come? But they're hot because they're fusing. So what allows them to fuse?
Perhaps just the gravity.
Yes, among other things. But the simplest explanation is because those stars are so massive, the force of gravity is unbelievably strong, which can bring those nuclei close enough together that they can fuse. You can't do that on Earth. Okay. Let's see. So how much energy is given off? So put this in perspective. E equals mc squared. This analysis expresses the mass in kilograms. C is the speed of light. 3 times 10 to the 8th meters per second, which makes c squared 9 times 10 to the 16th meters per second. So if I use up a milligram, if a milligram of mass is converted to energy, how much energy does that make? On the order of 10 to the 10th joules. Actually, this should say milligram. But principle, a lot of energy you get. Okay, so quick tell your neighbor which of the following elements would undergo fusion. Or could undergo fusion. So if we look on the periodic table, hydrogen, potassium doesn't show up in here. Potassium is number 19. So it's gonna show up about here. Could potassium.
And is breaking.
Yeah. On Earth, maybe not, but in stars, sure. Okay, which ones could undergo fission?
Yeah, uranium.
Uranium is big. So iron's not going to do anything. Potassium, no, and radium. Yeah. Okay, here's a question. Translate this. If you have 2 nuclear bombs of identical mass, which will give us the biggest explosion? So if you have a kilogram bomb with a kilogram of uranium-238, versus a kilogram of hydrogen? What's gonna give you the biggest bang? Hydrogen is, how come?
The stable, so it has the most energy.
So yeah, it's gonna, the biggest transition from here to here, plus you're gonna, in a kilogram of hydrogen, you have a lot of nuclei, right? Way more nuclei than you'd have in a kilogram of uranium. So a hydrogen bomb is for the size, much more powerful. It's a little ridiculous because why would you need or want a bomb more powerful than a fission bomb? Scary. Okay, question. Are all isotopes of an element equally stable? No. And I don't know the rules about what makes one isotope more stable than the other, but it does. In fact, there's this idea called the belt of stability that your textbook shows where they plot all the different types. There are isotopes that are in the belt of stability, and those are radioactive. Okay. Anything with an atomic number greater than 83, we call radioactive. But what does that mean if something is radioactive? What is a radioactive element? A radioactive element is one that will, on its own, with no help from us, undergo a nuclear reaction. If I hold a radioactive element in my hand, and wait long enough, it will undergo a nuclear reaction. So think about it. There's Marie Curie, and she's isolated all this radium, and it's undergoing radioactive decay all the time, so much so that it's continually glowing and giving off green photons. She had a closet in her house, and she would store the different vials of radioactive radium as it was glowing and beautiful. When she had dinner parties, she'd invite people to go in and stand in the closet to see it glow. She thought it was really cool. The wives of the scientists that she invited to go stand in the closet with her did not think that was cool. That's actually a real thing that happened. Yeah. Okay. Okay. So radioactive decay is a specific kind of nuclear reaction that happens spontaneously in nature without any human intervention. And a radioactive element is one that will undergo radioactive decay. What are the rules? In a radioactive decay or any kind of nuclear reaction, charge is conserved. So however many positive charges you have in the starting materials, you have to have that many in the products. However many nucleons you start with. So when you add up the mass numbers of all the starting materials and the mass numbers of all of the products, they have to be the same. Now, instead of conservation of mass or conservation of energy, conservation of mass energy, which really means that any mass change between when the mass goes down as you convert starting materials to products, the loss in mass that you see gets converted to energy that's given off. Okay, and why are we doing this as part of Unit 1? We're doing it because radioactive decay is always first order kinetics. Why would it be first order kinetics?
One molecule.
Yes, first order kinetics means in the rate determining step, it only involves one molecule, right? Nuclear decay involves a single nucleus, right? So it can only be first order because there's only ever one thing involved. Okay, so what does that mean about all of our equations and analyses for first order kinetics that you did lectures 1 through 3? They all apply to radioactive decay. Skip that one. So what kinds of radioactive decay is there? You have already learned about a specific kind of radioactive decay called alpha decay. When you learned about Rutherford Guilfoyle experiment in Chem 105, what we said is that Rutherford shot alpha particles through the gold foil. Where did those alpha particles come from? He had a chunk of radioactive polonium that was undergoing alpha decay and giving off alpha particles. So the source of the alpha particles that were being shot through the gold foil was a chunk of polonium. Interestingly enough, they didn't understand the health risks of radioactivity. And so they would just, carry the polonium around, it's stored in the drawer in the bench. And I watched a video, the kind of a scientific popularizing science thing where they took a Geiger counter. How many of you have ever seen or used a Geiger counter? So a Geiger counter, every time it experiences, it detects radioactivity. And the frequency of the blip, blip, blip tells you how hot, how radioactive something is. So if you hold the Geiger counter up to something and there's a low level of radioactivity, it goes blip, 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 blip. If there's a lot of radioactivity, it goes blip, 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 blip. And if there's really a lot, it goes, which is why when I worked with radioactive materials in my dissertation work, we'd say, that's screaming hot. That was the Geiger counter would scream. Okay, so take that back to polonium that they used in Rutherford's lab when they were studying the gold foil experiment in alpha decay. Today, you can take a Geiger counter to the lab that he was using, open the drawer, and put the Geiger counter down into the drawer, and it goes beep, 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 beep. It's still radioactive after all this time. Okay, so alpha decay. Rutherford was studying alpha decay, which is a radioactive element, a heavy element that's unstable because it's too big. One way for that nucleus to get smaller is to drop a chunk off of itself. And the chunk that it gives off is an alpha particle, which is 2 protons and 2 neutrons. Yes.
Aren't those two like super unstable?
It shouldn't say the most stable nucleus next to hydrogen. It should say dramatically more stable, is what it should say. But if we're starting with a heavy element like this, if it can break into helium, totally, it makes it more stable. We do see alpha decay happen, and I need to rephrase that and think about the right way to do it. Okay, how would you recognize alpha decay? So you are not going to have to look at an element and say, I think this element is going to undergo this particular kind of beta decay. You're not equipped to do that. I'm not equipped to do that. I'm not certain what level of training you would need in nuclear physics in order to be able to do that. So the only thing that you would have to do is to see a reaction and know whether it was alpha decay or not. So what's going to happen if they tell you that you produce either an alpha particle or a helium nucleus? That's pretty easy to tell that it's alpha decay, right? Could we just show you that? I would say radium 226 goes to radon 222. How would you know it was alpha decay? The mass number went down by 4, which is what happens when something gives off an alpha particle. So that's how you recognize it. Okay, the other kind, all of the, pretty much the rest of the nuclear reactions that are part of radioactive decay, we lump them all into what we call beta decay. It's called beta decay because it gives off or takes in a beta particle. One example of a beta particle would be an electron. But there are other kinds of beta particles called positrons. Group them all together. Okay. How you recognize beta decay? In beta decay, a proton becomes a neutron or a neutron becomes a proton. So what happens to the atomic number? It either goes up or down by 1. So in beta decay, an element can change into one below it on the periodic table or above it on the periodic table, which means the atomic number can go down 1 or up 1. What happens to the total number of nucleons in beta decay? It stays the same. So the mass number doesn't change, the atomic number does. Okay. So in beta decay, the atomic number can go up or down by 1. The mass number doesn't change. What happens if you have an isotope that's unstable because it maybe has too many neutrons? It can change the neutron into a proton, potentially can solve that problem. So how does that happen? How could a neutron change into a proton? So charge has to be conserved, total, right? So if in the nucleus, something neutral becomes something positive, how can that happen? It could release an electron, yeah. That is a kind of beta decay that sometimes is called electron emission. What would happen to the atomic number if that happened, if a proton becomes a neutron? So the number of protons goes down by 1, so the atomic number goes down by 1. Okay, is there another way? Well, can you change a proton into a neutron? What would have to happen to take a positive proton and make it a neutral neutron? It could take in an electron. Can that happen? Are there electrons in the region of the nucleus? So think about Chem 105 and the different orbitals. P orbitals don't have any electron density in the nucleus, right? S orbitals? Yes, they do. S orbitals do not have a node at the nucleus. There is electron density in the spatial region of the nucleus, and so a proton can potentially take in an electron to become a neutron. We call it electron capture. Now, there is a thing called a positron. It's like an electron, but positive. And if a proton gives up a positron, it's no longer positive, so then it becomes a neutron, right? Why don't we learn about positrons in chemistry? It doesn't last very long. So if you have beta decay that gives up a proton, what happens when if you have beta decay that gives up a positron, what happens to that positron when it encounters electron density? Proton plus an electron becomes, they cancel each other out. They make each other disappear. So if you have positron emission, that positron is released from the nucleus out into the orbital clouds around a nucleus. So what happens to it? Doesn't make it very far.
And is that what emits gamma rays or?
Gamma rays are different. Gamma rays is not strictly speaking a reaction, because a gamma ray is, gamma photons are given off when photon, too many rhyming words. A gamma photon is given off when an excited proton at a high energy level relaxes back down to a lower energy level inside the nucleus and gives up a gamma photon. Okay, so will you have to look at a nuclear reaction and recognize, is it alpha decay or beta decay? Yes. How did you recognize electron emission? If a neutron changes into a proton, you can read that from the change in the atomic number, right? Can't necessarily tell the difference between positron emission or electron capture unless the reaction tells you that you have a positive beta particle as a product or electron included as a reactant, right? Okay, how do we read these? Actually, let's do that on the recitation and that'll make more sense. Something to keep in mind is that what actually happens in nature when you have an unstable isotope that decays, or you undergo fission, you're going to create new radioactive isotopes that continue to decay. So for example, if you take uranium-238, it is radioactive. It will spontaneously on its own undergo alpha decay to form thorium-234. But then there's a whole series of, there's two different beta decay processes and then alpha decay. The isotopes decay from one to the other, to the other, to the other, to the other. We call that a radioactive decay process. What happens to the products of a fission reaction for a atomic bomb, for example? Once you do the original explosion, what you're left with is a bunch of other radioactive materials that continue to undergo radioactive decay. So I grew up in the 80s because I'm very old. And on television, there'd be all these programs about what will happen when the atomic bomb goes off. And they did a lot of talking about radioactive fallout. What radioactive fallout is all these other radioactive nuclei that get released after an atomic bomb that continue to filter down and do damage because of the continued decay process. Okay, yeah, so the question is, once it gets here, then lead-206 is not radioactive. It will eventually, over time, decay to something that isn't radioactive anymore. Okay, terminology that you need. In chemical reactions, we talk about starting materials and products, right? In nuclear chemistry, we talk about parent isotopes and daughter isotopes. What's the parent isotope? It's the starting material. What's the daughter isotope? It's the product. So if we're looking at this first alpha decay, uranium-238 is the parent, thorium-234 is the daughter. Okay, Josh asked about gamma decay. So gamma decay is considered a kind of decay, but it is not a nuclear reaction. If you have a high energy nucleus, some of those protons or neutrons will exist at high energy levels and then relax down to lower energy levels by giving off a photon. The photon that it gives off is a very high energy photon because the difference between the potential energies of those energy levels is huge, presumably because the nuclear strong force is so strong, you release a super high energy photon. But you're just releasing a photon, so atomic number doesn't change. No proton is getting changed into a neutron. The nucleus isn't coming apart at all. It's just going to lower energy. Okay. How do we identify what kind of decay something will undergo? You don't have to predict. If you're given this is the starting material and this is the product, you can figure it out. The difference between nuclear reactions and radioactive decay, I'm going to answer that. Radioactive decay happens spontaneously without any help from humans. We also have fission and fusion, which is an additional kind of nuclear reaction that is not radioactive decay. How will radioactive decay concepts apply to the rest of this course? You will use the equations for first order kinetics to analyze them. We are going to talk about spontaneous and non-spontaneous reactions at delta G. Remember in first lecture, we talked about delta G, free energy change. If radioactive decay processes are spontaneous and happen without any help from us, what does that say about the sign of delta G? It's negative. Okay, in those processes, heat is released. So what is the sign of delta H? Negative. For a lot of them, delta S is also positive. Okay. Spend a few minutes just down to number 4 material. 6 through 8 is what I really want you to work on. Yeah. If you want, sometimes you can distinguish between the It's not working for you. Okay. Good. It seems like the perfect way to do these.
Yeah.
Right in the PowerPoint.
And I have to go through it. Okay, so the prep time.
Let's connect this back to the equations that we use. What's the order of radioactive decay processes? First order. Why? There's only one nucleus involved, so there can only be one thing involved in the rate determining stuff. So it's always first order. Which means that everything you've learned about first order kinetics applies to radioactive decay. In fact, there is pretty much nothing new here. Okay, so what are the equations for first order kinetics? We have our first order rate equation. Integrate it to get the first order integrated rate equation. We can rearrange that on this. We can work on that to give us our half-life. Just looking at this line here. And we can also combine our half-life. This version of our integrated first order rate equation to get an equation that relates the percentage of starting material you have left to the number of half-lives that have passed. Okay, when we express those, for radioactive decay, all the same equations, that these equations are all expressed in terms of molar concentrations, right? Meaning that they apply to solutions of a substance. Are we dissolving radioactive substances? No. They're solids. So what do we do instead? We take the equations, and instead of expressing the amount in terms of molar concentration, we express the amount in terms of number of nuclei, number of particles, essentially. And the truth is, we don't even usually do that. We don't even usually talk about number of particles. What we usually talk about is the percentage of starting material we have left, or the fraction we have left, which is the NT. The number we have at a certain time divided by the number we start with is the fraction we have left. Now, the textbook takes this equation that you've seen before and just puts it in a slightly different rearranged form, which is this version. Sometimes that's a little easier to use. It's not new. It's just a different version of the equations that you've already. Okay, so the equations are the integrated form, which we don't usually have to use. So the rate would be the number of materials times the rate constant. And we don't even usually talk about the rate for radioactive decay. What do we usually use when we're talking about radioactive decay? We just talk about half-lives. Why would we do that? In part, a lot of these processes are really slow. So the half-lives are on the order of thousands to millions to billions of years. Okay, so we have that. Those are our equations. Number of radioactive gas, 20 minutes, how many half-lives have passed? So a quarter of the original gas is used up. Without using any equations, you can say, well, I know after one half-life, how much is used up? Half. After two half-lives have passed, how much is used up? A quarter. So you know that it's exactly two half-lives. Now, you can do this one because the time that they give you is exactly a certain number of half-lives, right? You won't always be given that. Sometimes the time you'll be given will be like 1.257 half-lives. And then what do? A little harder to predict. So how would you do it with equations? You would say, I can relate the fraction that I have left, the number of half-lives with this equation. The fraction that I have left is a quarter, 0.25. Time is 20 minutes. Plug that into the equation with the numbers, and you get the half-life is 10 minutes. So you knew that intuitively, but the math says the same thing. And you don't always know, you can't always do that math in your head because you're not always given a round number of half-lives. All right. Are you comfortable applying those calculations? It's just the same thing we've done before. Let's talk about that. We have 5 minutes left. It's probably more useful for you to work on recitation together and to find out the questions to ask yourselves and others. Slides are posted. So if you want to go through the math, it's all there. Watching me click for the next equation is probably not something.
So